So what does it take to create the most efficient AI infrastructure? Firmus has been on this mission since 2019, considering how we can address this problem. My name is Daniel Kearney. I'm the CTO of Firmus, and we are looking at addressing this problem with our model-to-grid architecture embodied by Project Southgate. To better understand this challenge, let's have a look at the ecosystem, all of the various different layers and components. From the model development to the grid energy, there are various different layers which constitute this opportunity. We're here in San Jose, the home of model development, but we often forget about the requirements, the energy requirements that underpin this. In this ecosystem, it's largely divided into two camps. Those who are primarily model aware and have a deep innate understanding of the compute signatures, training cycles, and inference requirements. And those that are more grid aware, more traditional data center infrastructure providers that understand power, signal, building out physical infrastructure, and cooling loops. However, the ecosystem has significantly evolved to systems of scale, requiring a much more holistic and system-level view of the problem. At Firmus, this underpins our strategy, model-to-grid, and our model-to-grid architecture. Let's decompose a little bit our model-to-grid situation, and let's understand a little bit more about why this is such an out-of-sync problem. The models that have been built today are operating at a far greater scale, running in microseconds, deployed at microseconds. However, on the energy side, we have communication timeframes of the order of minutes. As we grow in scale, and we've heard a lot about Giga-Scale AI factory requirements, we need to be more in sync and more communicative with the grid that responds to those very loads. Between the model and the grid are several layers which shape, define, and help deploy the infrastructure required to run these models. Now, to better understand the model, you really need to understand the innate electrical signals underneath. At Firmus, we spend a lot of time decoding and understanding these models. What you're seeing here are various rack-level signatures of workloads, power deviations normalized against the thermal design power of the GPU for a signal sample size of 10 seconds. Now, this looks like a very noisy signature running across a distributed AI infrastructure system. However, for Firmus, we decode these signals into discrete systems. We take it from noise to signal. Each individual signal, a veritable brainwave for an AI model, represents a unique intelligence path. The first model you see here is a dense model, pre-training, sustained power fluctuations for forward propagation, dropping down for more memory compute moments, and that constant fluctuation can actually, at gigascale, be the orders of tens of megawatts over microseconds in time. A significant challenge for future AI infrastructure developments. Then we see sparse models, rapid and random ramp up and ramp down of power. We see inference, batch-based inference, effectively coding workloads, pre-filling the work, and then distributing tokens in more regular form factors, but yet still fluctuating. At the bottom, you see inference queries, the classic chat queries that we're using today. Every model, every token goes into a different value of use, a different model type, producing different workloads. At scale, these compound and these matter. And that's the type of understanding that Firmus and the engineering team are developing. We've taken this 5-layer model-to-architecture approach, and we've decomposed it into the model-aware components and the grid-aware components. With these power signatures, we're able to better understand how energy can be managed. The workloads understanding allows us to offer our customers clear, frictionless AI platform to access the compute and orchestrate the workloads across the AI factory fabric. But also on the bottom, in the grid-aware portion, we're able to better design the hardware systems that are used to manage the energy, thermal and power. Specifically, the grid. So let's take a deeper look at the grid. And what is that grid of Project Southgate? So as we stand here in San Jose, we're actually 72 milliseconds away from a real opportunity with Project Southgate and an ecosystem that can address many of these challenges. Globally connected with a series of subsea cables, Australia represents a secure, geopolitically stable Western democracy that has all the attributes required to build AI factories at giga-scale. Let's start with the connectivity. Australia is well connected across many different subsea networks to Western US, Asia Pacific, and even to Europe, in the order of sub 200 milliseconds for all routes. As a region, Australia offers opportunity to scale AI factories and serve it to the world. As Jensen says, not every workload is latency sensitive. AI doesn't care where it goes to school. Underpinned by the connectivity is the electrical network. Australia has a very resilient and modern energy grid. Australia operates one of the largest wide-area synchronous electrical grids in the world, stretching from Queensland in the north through New South Wales, Canberra, Victoria, South Australia, and down to Tasmania. Every single transformer is interconnected and operating on 5 minutes dispatch and settlement periods, which is very unique for the world. This low latency communication allows AI factory operators that think with a model to grid mentality an opportunity to work as a true grid asset, not a grid liability. And this is actually some of the DNA of Firmus. Overlaid on this connected and energy-rich fabric is our AI factory network. Our Giga-Scale network of AI factories are deployed across the key regions of the states within Australia. Scaling up to 4 gigawatts of power beyond 2026, these multiple sites offer customers a multitude of options against various grid profiles to serve and train their workloads, scaling to 100,000 plus GPUs post 2026. Australia is well connected and well powered. Now let me take you to a specific node on the Project Southgate map. Tasmania. This is where Firmus was founded back in 2019. We have built deep partnerships with local government and industries to establish what will be our flagship AI factory in 2026. The Tasmanian government last year announced the Green AI Energy Zone. It's an area of renewable energy that is primed to support future expansion with AI factories. Offering one of the most unique grids in the world, Tasmania has 100% renewable energy as of today, 80% firm hydropower supported by 18% wind and solar, with more renewable energies planned to come online in the coming years. It's a very unique position for an AI factory development area. And not only does it have grid capacity today, it has excess capacity planned for the future coming years, with over 200% renewable grid power by 2040. That's right, Tasmania has twice the domestic consumption of electricity and gives Project Southgate plenty of headroom to expand. So what are we doing here? Launceston will be the home in 2026 of over 36,000 Grace Blackwell 300 GPUs. We'll be developing these with an average design PUE of less than 1.15, incredibly efficient, every single watt converted into a unit of intelligence. That represents 1,440 petaflops of compute, or a billion mathematical operations every second. If you blink, by the time you open your eyes, there will be over 1,000 GPT queries completed. One of the largest compute installations in the Southern Hemisphere at the end of 2026, and built from model to grid, co-designed, deeply co-designed and vertically aware. Launceston is well up and running. We have completed some of the earthworks already. We're already onto piling the initial stages of stage 1. The total capacity represents up to 90 megawatts in total across 2 stages, complete by the end of the year. Beyond 2026, we'll continue our expansion through northern Tasmania in Georgetown, where we'll be installing over 70,000 Vera Rubin 200 systems, again, at an even more impressive 1.15 PUE, and that will represent a tripling of the actual compute capacity. So we're very excited about the developments of interconnecting these gigascale factories. But above all, this represents the blueprint of how we will be rolling out efficient, dense, gigascale factories across the Project Southgate portfolio. So now that we've understood the grid and the renewable energy, the sites, and our planned expansion for 2026, let's consider what is actually inside a Firmus AI factory. From a model-to-grid approach, doesn't just consider the environment, it considers every single touch point in both hardware and software where energy is consumed and transformed. Our intelligent power and thermal management is a key factor in this. So the Firmus Hypercube, this is the atomic building block of AI for Firmus AI factories and our intelligent scaling unit. Every design decision at Firmus starts at the accelerated compute fabric. From the GPU, we design outwards, not inwards. It wraps, the GPU and the systems are wrapped around by intelligent power and thermal management. The Hypercube scaling unit is 10 megawatts with N+1 redundancy, with scalable up to 12 megawatts. And critically, and most critically, it's designed for multi-generations. We do not design point-in-time solutions. The Hypercube is designed today for Grace Blackwell, Vera Rubin Ultra, all the way through to Feynman. We are designing and engineering out obsolescence. We are designing for the future, and we're designing for scale. Another key point about the Hypercube is that much of it is designed and built and tested off-site. We do factory acceptance testing, load and hydrostatic and fluid flow testing off-site, compressing the commissioning time for when we deploy. The Hypercube not just represents a more dense form factor, it compresses time and it allows us to provide a much faster dirt-to-token time, which is critical. At Firmus, engineering matters and speed matters disproportionately. We know that we're in a race to deploy large-scale systems quickly, and the Hypercube is one of those vehicles. Extreme co-design in both power and thermal management. To learn more about the Hypercube, stop by our booth 1831, where we have a team of engineers that will be happy to walk you through some of the key components. Southgate isn't just about where we put the AI factories. It's also about securing the supply chain, and securing the supply chain in Australia. We've built a manufacturing ecosystem in Australia that supports Southgate, and it gives our customers something rare in this industry, a sovereign supply chain for AI infrastructure. Thanks to our partnership with Benmax, we've been able to co-design and innovate rapidly on this Hypercube design, and we continue to expand our ecosystem of design opportunities across the AI infrastructure stack. From dirt to token, from breaking ground to producing intelligent machines, we are considering every aspect of this design. So here it is, Project Southgate, the complete picture. We've populated the perfect AI destination, optically connected, a resilient and modern energy grid with a strong portfolio of renewable energy and more to come, a secure supply chain at giga-scale compute, connected to the world. Project Southgate is not just one of these things, it's all of them, designed together from model to grid. It's also important to consider that this represents the ecosystem for which we will be developing more of the accelerated compute. So you've seen in the last few days about how rich accelerated compute has become. The GPU is no longer the sole contender in compute processes. The Vera-Rubin platform has over 7 different silicon devices, from the CPU, DPU, NVLink switch, Bluefield, and Spectrum-X switch. There's a whole array of dedicated fit-for-purpose devices that consume energy to optimize energy to token conversion. And thanks to our partnership with NVIDIA, we have been deeply co-designing and co-engineering with them for a number of years. We're very proud to announce this week to have been chosen as a select partner for the Vera CPU standalone device, which we'll be implementing and incorporating into Project Southgate in the coming rollouts. As of yesterday, we've also announced a press release with NVIDIA that we're going to collaborate deeper on DSX blueprints with our model-to-grid architecture. So using our deep software and hardware understanding, we're going to be developing what will be the reference architecture and the blueprint for how large-scale AI factories should be developed and deployed at speed. We are also very much involved in Omniverse, so we're using some Omniverse for our particular designs and capabilities. This all allows us, this ecosystem, this rich ecosystem, fundamentally is about providing tokens to our customers. How are we able to develop and deploy models at scale that serve customers using GPU as a bare metal service or as a virtual machine or GPU abstraction? We continue to be model aware and develop Firmus AI Cloud and a rich orchestration platform to support customers. We are developing an orchestration and observability platform for over 1 million GPUs scale. At Firmus, we are thinking hyperscale. And in this model-to-grid ecosystem, it's a very, very rich data ecosystem. It is a data flywheel. The more we deploy across Project Southgate, the more data we pull from model to grid, we enrich our operations, we enrich our design, and we codify these systems to become more strong, more resilient, and more efficient from model to grid. And efficiency for us is not just about energy. It's about cost. It's about supply chain. It's about speed. It's about de-risk. Every single aspect needs to be considered to truly build this, because AI is not an aggregation of discrete technologies. The AI factory is a co-designed machine. Just like co-design has been applied to other systems and devices, the AI factory happens to be at building scale, at gigawatt scale, interconnected and ready to serve tokens to the world. So this engineering relationship with NVIDIA is also really important for us because it allows us to stay abreast of the changes, the constant innovation in hardware, in accelerated compute, in model development. Earlier on, I showed you about various different model types, various signatures. They were simply representative, not an exhaustive list of what's possible. Every time new models are deployed, we're polling, we're decoding what those model architectures look like, and we're bringing them into our knowledge of how to better run AI infrastructure. From model to grid, we're really watching how we can maximize every single watt and transform that into a token and a value for our customers. Let me give you an example of what the future looks like for Project Southgate and how we're thinking about this data ecosystem and how we continue to optimize it. We will take traditional basis of designs, turn them into machine-readable format. We'll take an innate understanding of rack-level workloads and signatures. We will look at grid data, historical and current, including tariffs, and be able to pull APIs in real time into our system. Our deep engineering knowledge in thermal management and electrical engineering, we will run high-fidelity simulations in the Omniverse ecosystem using ANSYS, CFD, and one-dimensional analysis will be run against some of our designs, and then reduced down to, in reduced order models, the inputs will be taken into our digital twin. We'll also run electrical simulations using ETAP identifying power scenarios, fault scenarios, and ultimately proving out concepts before they're ever born. This is the foundation of the digital twin, which feeds into the Firmus AI factory optimization engine. A large code base that we've developed internally and will continue to enrich, where we're taking all of these optimizations and running them against scenario analysis, maximizing grid to token efficiency, optimizing cost, and continuing to drive better operational performance. Our current cost to build an AI factory is $5 million US per megawatt. $5 million US per megawatt to build our AI factory, excluding compute. And that's the starting point. This data flywheel, these optimization factors will continue to drive where we can provide relevant AI factory infrastructure that acknowledges the grid, the climatic conditions, and provides more opportunity for us to run even more efficiencies. The Hypercube unlocks more opportunity to move the thermal load into liquid. Operating at 45 degrees, how do we optimize the adiabatic systems, the external heat rejection points? How do we consider right-sizing BESS even more, battery energy storage or energy storage in general? How do we take watts and put them straight to compute, not stranding power? We want to run a very lean and optimized machine, and this is the start of the flywheel that will be used with a data-driven position. The outcome for our business, of course, will be traditional operations. We will be providing more dashboards and reports for internal and external parties. Leveraging NVIDIA's Omniverse ecosystem, we'll be able to virtualize Project Southgate sites before their dirt is even turned, emulating what conditions we will expect and getting match fit for go-live day. Most exciting, Firmus runs a very competent operations system. Currently, we're operating already some NVIDIA infrastructure in Singapore, and now we have the chance to emulate future operation sites before they turn on, scenario analysis, fault injection, prepare our operations team, and codify where we can. Taking humans out of the loop for giga-scale factories is critical. How do we develop systems that allow us to scale at hyperscale and stay resilient and strong? We are currently operating at 4 nines of uptime for our systems, and we're going to push that even further. So the operations playbook, through this data-driven and virtualized approach, is going to drive even more capability from day one. We don't need to have a long learning curve to practice these systems. Probably more excitingly, I think, is the opportunity to develop more synthetic data, to develop the capability to have agents operating within our software layer, our AI factory orchestration layer. How are we able to reconcile between challenges in model, grid, power, and thermal management? How do we become more adaptive to the requirements of the model? Models will evolve. We need to stay abreast of what those developments are. How do we stay future-proof as a system? While the physical systems may seem constrained, there's a lot of opportunity to use software intelligence and agentic capabilities by developing this synthetic data and putting it to work within our AI factory. So it's probably one of the most exciting areas, I think, this flywheel that Project Southgate will provide at Giga-Scale, which will only provide a more richer customer experience and resilient experience. So that represents the AI factory vision, the radical shift for Australia, and indeed what we believe is a blueprint for global AI deployment. We need to be intelligent about compute. We need to be intelligent about energy as we are about compute. And this is the main philosophy, converting every watt into a token value. So with that, I'd like to thank you very much. I'll pause for questions.
All right, thank you very much. If we can have any questions out there? Okay.
Thanks, Dan. Great presentation.
Well, hold on one second. Let me get you the mic.
No problem. Thanks, Dan. Could you just expand a little bit more around the impact that AI factories are going to have on grids and just how you're intending to manage that. Yeah, it'd be good to understand, because there's been a lot of talk around, certainly in the US, around the grids and how they're functioning with all the load that's coming on.
Yeah, certainly. It's a great question. It's a question that every, I guess, large-scale operator is challenged with. So the DNA of Firmus, and actually, incidentally, the company started as Firmus Grid. So driving accelerated compute and polling the grid to understand its frequency at any point in time and responding to that. So I think one of the advantages, first of all, of Project Southgate is that dispatch and settlement period of 5 minutes, that frequent polling that's happening, so that we're able to understand what position the grid is in. When we see a workload coming online, we can see it because we are model aware, because we are orchestrator aware. We see what large-scale model is coming. Is the model going to operate in a synchronous fashion, which means all of my GPUs are operating together, or is it going to be sliced across the infrastructure and come on in phased points? That little bit of detail is important, because knowledge of the load is what we need to do in order to manage the synchronization between the grid. So today, there's a huge amount of stranded power that's been used within these systems. Our awareness of the grid requirements plus the model requirements will allow us to phase that transition in. We've deep knowledge within the company as well about how we manage the power. How do we use some of the in-rack power capabilities through power shaping? We can manage ramp rates, we can manage ramp down rates, and including some of the capacitor capabilities. But it's really about that communication sync between the model coming online, the type of model and the requirements it will have, and how we can kind of communicate with the grid and bring on that workload in a controlled fashion. Of course, we have energy storage within our systems, and we can use that in sync with that. So that's the intelligent power coupled with that model-aware orchestration capability.
Hey, Dan, thanks. I heard a number you mentioned, $5 million per megawatt.
Yeah.
That's a good number. Does that include construction, land, transformer, MEP? Is that all of the above?
We have a breakout of the detail of the that exact number. I think one of the key things about the model-to-grid architecture is traditionally everybody is playing at a various different layer in the ecosystem. Everybody is compounding engineering compounded margins of conservability in each layer and economic margins in each layer. The vertically integrated co-design approach is allowing us to remove some of those margins. So we're producing our own CDU. We're producing, we're working closely with partners to develop powertrain units, and you can talk more about those at the booth. We have some examples of what that is. And of course, we have more in the stack, but it's a representative number of everything X compute. US,
So
$5 million US per megawatt.
So I'm based in, I have a project in Indonesia that we're continuing to build out. So do you work on a sort of a consulting basis, or do you have to basically do turnkey? What's the
Firmus designed, build, and operate AI factories.
Ah, I see. So
the Launceston example is one of a greenfield where we're literally doing the full design of the AI factory. Working with, obviously, construction partners. We're not a construction company. We leverage the partner ecosystem to physically build it. But that example of the Hypercube, that is part of our exclusive supply chain. That is a Firmus piece that we're going to build, and we continue to enrich in terms of its modularity. That comes into a site, we deploy it, and that becomes the inners of the AI factory. And then, of course, the compute and network arrives, and we stand it all up. Our software teams come in, commission it, and then we serve our customers in whatever form factor, long tenured contracts as a cloud operator. So we're an AI factory builder and a cloud operator.
I see. So would you, let's say I'm a data center developer as well. I mean, we're an operator as well. I mean, is there room to partner with people like us, or do you want to do everything yourselves?
One thing that's important, again, coming back to the actual output of the thing, it's very important that we're maximizing every watt. And to do that, it does require extreme co-design. So we would certainly entertain conversations, and we have Toby at the back who can talk more about how we partner with various people in our ecosystem. While we're deeply vertically integrated, we do horizontally partner in areas of the stack that make sense. So,
Great, thanks.
Thank you.
Okay, we could certainly.
One question about the financing of these, the sovereign infrastructure. Is it like public-private partnerships or government-financed?
Yeah, so we have secured debt financing and equity financing to support our journey around Project Southgate. And some of that is publicly out there already. So NVIDIA has been a very supportive partner, both in equity and in engineering. And we're continuing to help to grow that journey to support Project Southgate.
Thanks, Dan. You talked about the Australian grid being dispatched in sort of 5-minute intervals. Is that unique, or is that something that happens around, like in the US? Is it a much longer dispatch time? And what does that therefore mean for, I guess, your ability to bring tokens to market more cheaply and more efficiently, and also help the grid? Because obviously we've got massive constraints on power.
Yes, exactly. Dispatch in 5 minutes is unique, but what's even more unique is settlement in 5 minutes. So it's dispatch and settlement in 5-minute increments. That is unique. I mean, the grids around the world, even when we say the US grid is actually many grids, right? And as is Australia, but the method of the Australian electricity market operator, AMO, they operate this 5-minute dispatch and settlement, which is unique, which is exactly why model to grid is so perfectly poised for Australia to be a blueprint for how grids should operate with AI factories. If we go on the journey that Jensen is showing that we will go on, we will be scaling to very large AI compute systems. These are engines of intelligence. They will power the future economy, but they have to be well managed within a grid ecosystem. Therefore, we need to break down the communication layers between sink and source, between energy supply and energy demand. That's the communication latency piece, the minute portion that I mentioned. So the Australian grid is definitely modern. It's showing the way. It's also showing potentially how other grids may need to think about communicating as with AI factories. So we think about AI factories as a Firmus. We want to be a true grid asset, not a grid liability, not an unknown node on a very complex network. The wide area synchronous grid that I mentioned from Queensland to Tasmania is over 5,000 kilometers. There are many different types of workloads, from smelters to large industrial complexes. And of course, now we're planning a Giga-Scale network. We have an obligation to step into that grid and break down those communications. And I think that's a mentality and a philosophy that applies to every grid around the world. Now, I'm not saying every grid around the world can potentially do it. I think everybody in this room would acknowledge that generally electrical infrastructure has not been invested in the majority of places for quite a while. So therefore, there is that need to now fully invest in that. But we are lucky that there are places like Southern Australia who have modernized some of their grid and represent an amazing ecosystem for AI factories. And I will add that last year there was over 5,000 gigawatt hours of utility PV solar produced in Australia. Lots of land, lots of sun. But a renewable energy on your grid now brings an uncertainty and an intermittency. We don't want to have more of that on the AI side. So when we have two imbalances, there's obviously going to be loss of energy, wasted energy, stranded energy. So we're very much about making sure that synchronization between grid and AI factory is present. And it takes people to start leading the way. I always think that governments have to step in when private industry doesn't do what it's supposed to do, right? And we know that this is the right thing to do. If we're wasting energy and not right-sizing as we should be, then we need to be actively taking a role in that. So that's really why Firmus is so mission-driven on efficient AI infrastructure.
Thanks, Dan. Just a question on your recent announcement, the JV with NVIDIA to build grid software, and the implications of that. Will that be rolled out sort of globally, or will it be specific to Australian requirements? Yeah, the DSX blueprints, for those who don't know, DSX is probably not the best person to explain exactly as a non-NVIDIA person, but it's representing the framework for how AI factories should be built at Giga-Scale, right? And within that, there is a certain set of blueprints, how infrastructure should be combined, how it should be deployed.
And on top of that, there's lots of opportunities for intelligence. And our model-to-grid software will provide that grid awareness piece. Firmus Grid was founded, as I mentioned already, with an understanding of the DFDT, the frequency change in response to the grid. That's a very natural part of the DSX story. Making grids interface, the interface with the AI factory has to be well understood. So we'll be bringing that into the conversations and the deployments with DSX. That will hopefully become a global blueprint. We saw on Monday Jensen talking about the DSX blueprints, so looking forward to developing that deeply with NVIDIA. So this is very much a co-engineering story with them, so we're excited about that.
All right. Any other questions out there? I think we should give Daniel another round of applause.